Undercatch. So I'm here, though I'm just going to show you a little bit of my research, which is verification, actually. So I'm going to talk about the adjustment of wind-induced solid precipitation undercatch in the operational verification practices. And so I'm going to acknowledge my co-authors, Eva Mekis and Morten Kalsø from Norway. And I also want to thank Visa Forten, Frank Lespinas, and Jason Milbrand. So I have a storyline. Essentially, the storyline is very simple. I'm going to show you an issue, the solution that we found, and the results associated to that. So the issue, so solid precipitation, winter precipitation measurements from standard instrumentations are affected by the undercatch of solid precipitations when it's windy. So verification against these underestimated measurements leads to an enhanced diagnosis of over-forecast for our NWP systems. So here you see an example for the Canadian deterministic prediction system at 3 kilometers, 10 kilometers, and 25 kilometers that were running during the winter SOP over Fennoscandia or over North America, everything north of 60 degrees, and they systematically have this positive frequency bias index. So what do we do? Well, we quality controls of some operational verification systems, our, for example, flags the solid precipitation measurements in windy conditions so that they are removed before we perform the verification. So this is the verification sample size, and you see it's diminished a bit, but not too bad, just at 20%. But if you zoom in and you look on the precipitation events that happened that winter, and you see how much this is removed by our quality control, well, this selective screening essentially estimates all the major snowstorms, which usually occurs in windy conditions, right? So we have a decrease of 80% of the precipitations sampled in the verification. And this is a huge issue, okay? Because as a result, most of the heat events are not scored. The false alarm dominates the scores. And essentially, once again, we have the wrong diagnosis of what is really the forecast quality. So here you see that with quality control, we have much worse scores than without quality controls. So this is a problem. This is a no-go, essentially. We need to address it. So here we go, the solution. So the WMO solid precipitation intercomparison experiment, or SPICE, performed a multi-site intercomparison, and they evaluated essentially how the different instruments for measuring precipitations performed. So they did a comparison with what they call the double fence automated references, that is this one with 2 fences. And this is considered the truth in their estimation, and essentially with comparison with what was measured in the normal gauges, they could find out an estimation of the catch efficiency or of the undercatch. So they've developed these adjustment functions to correct the solid precipitation undercatch under windy conditions. And there are different formulations, but they more or less all work similarly. So this is how it looks, the catch efficiency. So the estimated catch efficiency depends on the temperature. This is for minus 10 degrees, and on the wind speed on the x-axis. The catch efficiency is a curve that decreases, starts from 1 and decreases. And it depends also on the gauge height or the shielding, the type of shielding that is at the gauge. So for example, for the unshielded, I have a more aggressive adjusted functions. For the one with a single altered shield, I have a less aggressive adjustments. And they also depends on the site characteristics and local climatology. So here I have in blue what they call the universal adjustments, and this has been estimated from several sites in different locations in the north. But then I pull out 2 particular sites. So Dankila in red, which is in a forested environment, so it's naturally sheltered. So you see the adjustment is less aggressive. And then I pick Aucalisiste, that is instead in a very windy locations on the top of the mountain, and here you have a very strong adjustment. So there is a large span on what you could obtain applying these different adjustments, right? So let's see some results. So prior verifications, I adjust the solid precipitation undercatch by dividing the observed measurements with the catch efficiency. So this is an example. So the black line is the frequency bias index before I perform the adjustments, and then all the blue lines are what I obtain, the frequency bias index, after I perform this adjustment. So obviously it decreases. In this case, I apply a bulk adjustment to all stations. In the reality, I know each stations which shielding they have, which height the measurements is. So this is actually applied to the synoptic station. So really the dotted line is the most likely outcome. Most of them have a single alter shielding and wind measurements at 10-meter height. So now let's look at the other panel. This is 4 single alter at 10 meters with wind measurements at 10 meters. I have the different locations, and this is really the major source of uncertainty. Okay, so let me just put it on one slide. There is a large uncertainty associated with the adjustment, and an estimate ought to be provided along with the verification results on what we could obtain. Still, all the adjustments points in the same directions, right? Essentially, they correct an underestimation of the observation, so essentially our bias goes down. The over-forecast goes down. So the direction is similar, like climate change, but there is an uncertainty that we need to provide, right? The most significant source of the uncertainty relates not to the transfer functions, but to the individual site characteristics and their local climatology, which possibly mirror, and I'm going to get back to this, the microphysical characteristics of the hydrometeors prevailing at the individual sites. Like big snowflakes are going to be blown away more than like a little ice pellets, right? Okay, so results. We have verified the 3 Canadian deterministic prediction systems that were running at the time of YOP. This is the winter precipitations. We have 2 domains. Fennoscandia is on the top 2 panels, and North America is on the bottom panels. This is the frequency bias index, and this is the threat score. So as expected, the over forecast is reduced, so the black line is without the adjustments, and when you adjust, you have a decrease of it. Whereas the accuracy not always is improved. In this case, in Fennoscandia, we found better accuracy, but not in North America. So this is the result. And if you want to see the other models, well, I have also CAPS and GDPS on the posters. So I have a posters in the hall with all the models. I showed RDPS, but they all perform similarly, essentially. Summary. So we had an issue. NWP systems, systematic winter precipitation over forecast is artificially inflated by the undercatch of solid precipitation in windy conditions. We have a solution, which is the WMO-SPICE adjustment functions that mitigate the effect of this solid precipitation undercatch and enable to obtain a more reliable and informative verification, for example, for who is developing the models. Maybe we are not doing that bad as we think, right? Results, well, I already stated my results. Essentially, the over forecast is reduced, but the accuracy is not always improved. And this is an exercise that we did in different people collaborating within YOP. So there is a poster by Morten Kolso that is hanging there. You come and see it. And there is also a nice paper that Morten wrote on it. Good. So recommendations and future work. Our recommendations for operational environment is to adjust the solid precipitation measurements rather than removing the observations from the verification samples. I show you what happened. And though an estimate of the uncertainty of the verification results ought to be provided, and this uncertainty is inherited from the observation uncertainty and a bit the adjustment. Okay? So future work includes developing an adjustment functions for each individual stations that we have at least in Canada, for a verification and assimilation. So this is something we want to address with the Kappa team, which is the Canadian precipitation analysis. The second future work is raised by that comment that I made before, is that the catch efficiency is likely different depending on the microphysics of the hydrometeors that are falling, right? So we would like to investigate and eventually develop a dynamic adjusted functions, which depends on the different precipitating hydrometers. So actually, you can even model the undercatch with the models because you have the different types. So we'll start from there and we'll move forward. So this is all I have.
Thanks very much, Barbara. Any questions in the room or online? Microphone? No, Tanya, can you use the microphone, please?
How do you develop that, that site-specific adjustment factor, and is it wind-dependent?
So that was done within SPICE. So essentially, they had a lot of measurements from different type of gauges, unshielded, single alter shielded, and Gainer and Pluvio. So they had a bunch of instruments, and they did this intercomparison. So this is a long project. Like it's all in the report of Nitu et al. 2018.
I mean, it seems like a really important thing because measurement of precipitation is so difficult, and it implies that it's sort of a calibration process in each spot, each site. And each site should go through a calibration process to have these site-specific adjustments.
Yeah, they did it by site, and so they have different adjustment functions for each site. But what we think now is that probably, because you cannot do it for every site, right? So what we think is to try to address it with the different type of hydrometers.
I mean, actually, from a measurement standpoint, it sounds like eventually you really would want to do it for every site, and that should be a standard calibration for any precipitation measurement site. But that's really neat.
Okay.
Any other questions? That was a tie, I think. Go ahead. Could you use the microphone? I go to the runner.
Hi, Barbara. I had the pleasure of working with Radhika before I retired, and the question I have as a forecaster is, has there been discussions with the operational forecasters to actually incorporate even the rough adjustments into the forecast as part of their model assessment? And the second thing is, I set up a COCORAS network in Atlantic Canada because of this problem, because most of our observing sites are at airports that are really exposed to the wind. Is there any, and the next question would be a discussion with the Meteorological Service to actually locate snow measurements in more sheltered locations like people's backyards. But anyways, but I'm just wondering about the conversations with the operational forecasters.
Me being into the operational centers, I have conversated with myself, and we are doing it. So we are actually, it's already in our verification systems, the universal adjustment, but we at the same time, the Kappa team wants to correct them at sources because they want also to assimilate it, right?
Right, but I'm talking about the public forecasters.
The public forecasters, no, I'm not there yet, so I will follow up on that. Thanks.
Is it a quick question? Or
in regards to your question about potential dependency on local hydrometeors, was any effort made to account for that presumably changes at most sites seasonally? Is that a future research effort, or is that already incorporated into the SPICE work?
Actually,
Thank you.
It's a future, for me, it's a future research, but maybe it has been already done. But I know that Martin has already kind of, played a bit with the fact that the model can estimate the undercatch, essentially. So they can, instead of giving you what they think is the precipitation, they can give you what they think the gauge measures accounting for the undercatch. So I don't know, we'll go in all directions, but it's like it's ongoing research.
Thank you.